Okay, second of two videos here. We previously went over finding the Pythagorean identity, solving for either sine squared or cosine squared, and using it to do an integral like this. So let's go down and do one that has a couple more things that we have to keep in mind as we go through and solve it. So we're going to do the integral of sine to the fifth of x times cosine squared x dx. So given what I said up above in terms of like getting the du piece out, can you figure out what example 2, what piece we're going to leave as the du? Hopefully you said, well, sine there is raised to the fifth power. So I'm going to write this as the integral of sine, not squared, of sine x times sine to the fourth of x dx. Come on. Times cosine squared x dx. So, now what I do, we're going to go ahead and use, maybe I will copy and paste this. All right, there we go. So, what I want you to see here is that this right here is going to be the du part. So, and this cosine is going to be a u, so I need to convert this piece right here. So I'm going to do some side work over here for that. Sine to the fourth of x is the same as sine, come on, little, sine squared x squared. Come on. All right, so, what I can do is use the fact that sine squared theta is 1 minus cosine squared theta, and that's going to replace this inner piece right here. So what's that going to give me? Bracket 1 minus cosine squared x, close bracket, squared. And I'm not going to bother foiling this in its current form because I think you'll see that if I wait, it's a lot easier if we transfer over to u's first. So I am going to replace that sine squared x, right, or sine to the fourth x, with a 1 minus cosine squared x squared. So let's go ahead and write that. We get the integral of this sine x stays there. This sine to the fourth x gets replaced with 1 minus cosine squared x, close, squared, times another cosine squared x with a dx. Now, this is the spot where I suggest that you actually do your u substitution here. If you do use substitution here, then it's a lot easier to deal with this foiling stuff. Sometimes people will go ahead and FOIL this out in cosines and then combine them with this, but I think that's more complicated and more error prone. So what we're going to do now is let our u equal cosine, come on, pen, cosine x, and that makes my du equal to a negative, don't forget that negative, sine x. With a dx, I can put it there if I want to. All right, so notice we have a cosine and a cosine. That's going to get a u. And then I've got a sine that's going to become it's going to be a negative du. So when I do all my substitution in, I'm going to put my negative from the du out front, integral. I'm going to write the first two pieces, or sorry, I'm going to save this piece for the end. So I'm going to write open parenthesis 1 minus u squared, close parenthesis, squared. That is this written with u's. Now I got to do this cosine squared, so that's another u squared, times a du. This du is the sine, which is this, and then remember I got that negative out front to balance everything. So from here, I need to simplify or FOIL out. and then simplify. I need to change the way it looks first before I integrate. Sometimes we get like fancy little nice tricks, but this one we just got to algebraically manipulate the inside of the integral in order to be able to do power rule. So the squared piece gives me 1 minus 2u squared plus u to the 4th, close. That is this rewritten. So notice I still have that u squared on the side. So times u squared du. Don't forget the negative. So it's negative. And now I need to FOIL or distribute this u squared into those three pieces. So what I get when I do that, I get u squared minus 2u to the 4th plus u to the 6th du. And now it's in a form in which I can do my definite or do my integral. So I'm going to get u to the 3rd times 1/3. And what I'm going to do is distribute this negative into everything. So this term's going to be negative. I'm going to get a double negative on this one. So I'm going to get 2. It's going to go up to a 5th power. So I'll write over 5 u to the 5th. Plus, all right, this one's, so this one's not plus because I'm distributing my negative in. 1/7 u to the 7th plus c. And then the last thing I got to do is sub my u's back in. Notice u was a cosine x. So what am I going to get? Negative 1/3 cosine, come on, cubed x plus 2 over 5 cosine to the 5th x minus 1 over 7 sine to the 7th x plus a constant. And that's it. I've got my integral. Again, what I sort of said in the last video is that I'll zoom out so we can see the whole thing. Previously, with the techniques that we had, this was a integral that would have, I don't know what maybe, I think maybe the instinctual thing to try here is to try to do integration by parts. And I don't know, maybe we can do this by integration by parts, but that's going to get really messy. So hopefully you see now that we can do this quick substitution to using the Pythagorean identity to calculate this integral in a pretty quick way. Okay, so we actually have time for one more problem here, so I'm going to go ahead and do one more. This is example 3. And this is the integral of secant to the 4th of x times tan x dx. So one thing you have to know here is that the derivative of tangent of x is equal to secant squared x. We could do, there's actually, so looking at this now, there are other ways to do this one, as is often the case in math. And maybe you see another way to do a u sub here. I'm going to use this as an example to show you how to do a different type of trigonometric integration. But here we go. Tan prime is secant squared x. So let's go back up to the top here where we did all our triangle work. Do you remember when we had o squared plus a squared is h squared? And I divided by a squared to get tan squared of theta plus 1 is secant squared theta. You should be able to do that. We're going to go ahead and use that down below here for this integral. And if you understood what we did in the previous one, then this one should be pretty straightforward. So here's the deal. Tan derives to secant squared x. When I was up here previously, we always tried to separate this out so that the du was there. Now, the du of a sine or a cosine is always a sine or a cosine. It's always to the single power. So when I kind of separated this into two pieces, I left it as sine to the first power. Come down here, I've got secant to the 4th. I can separate that out into a lot of things, but because tan derives to secant squared x, I'm going to rewrite this as the integral of secant squared x times another secant squared x times my tan x. And the reason I'm doing that is because I'm targeting this piece right here. Whoops. This piece right here to be my du. I should put a dx right there. All right, so here's what we're going to do. This, I'll go to red. This piece is secant squared x. I'm going to replace it with a 1 plus a tan squared x. So let's do that. This is the integral, come on, of secant, come on, little pen, squared x. That's the one that's double underlined in green, times tan, come on, pen, gosh, squared x plus 1, close, times the other tan x with a dx. Come on. All right, so what did I do? I took this red box, which was, I know that secant squared theta is tan squared theta plus 1, so we just replaced the thetas with x's and popped over to this. So that became a tan squared x plus 1. So from here, I can start doing my u sub. I'm going to let my u equal tan x. Then my du, what's the derivative of tangent? I said we had to know that above, is secant squared x with a dx. So when I do my substitution here, all the tans are going to become u's. And then this right here, the secant squared, is going to become part of my du. So what am I going to get? I'm going to get the integral of, open parentheses, u squared plus 1. That is the first, my pen's really bothering me today. That's this with the tan just replaced with a u, times u, because that's a tan, times my du. From there, I can distribute. I get the integral of u cubed plus u du. That's easy to integrate with power rule. That's 1/4 u to the 4th plus 1/2 u squared plus a c. And then my last step is just to sub my tans back in. So what do we get? We get 1/4 tan to the 4th plus 1/2 tan squared plus a constant. Bam. That's it. So hopefully you see how we can do this substitution, this trigonometric substitution, using the Pythagorean identities with when I have secants and tans. I'm curious if any of you can see a way that you can use the derivative of secant to do this integral in a different way. And think about it. What's the derivative of secant? It's secant tangent. I have some secant tangents in here. And then I encourage you to say, what would that integrate to? And how is that related to this right here? And that's more complicated than I can get to in the just over a minute that I have left. But this method works. I think it's easy. Yeah, hopefully you are doing okay with this. I'll see you all soon. Peace.